So, yeah, I guess we can start recording. Yeah, so again, hopefully everyone enjoyed the break. We're almost at the end of the semester and the course. Maybe just before we begin, in case you didn't see it already, remember that we have the midterm. There's a midterm on Monday. So you can read the announcement here, but the practice, like the solutions to the practice exams can already be found on the website. So you can go there if you just want to compare what you did with the solutions. The final, yeah, the final is on the, actually 2 weeks from today, is on the 16th. In your case, it's at night from 8 to 11, but I'll post, like, the announcement for the final will probably show up on the website the day after this exam, so it should be there on Tuesday of next week. So, but yes, it's I can write it here. It's December 16 from 8 p.m. to 11 p.m. For the online class. Yeah, for the online class, correct. It is online as because you are in this online thing. So yeah, it's through my lab.
What if I have a conflict?
Well, you, like, there's a makeup. I mean, like, it works like as any other exam. So yeah, if someone has a conflict, you just have to email me and I'll tell you. I have to check the date for the makeup, but yeah, there's a makeup. So yeah, it still will respond as yes. So right, so that's like, but again, like the announcement on the final, I mean, like, it is the final, so there's not too much to say besides that it's cumulative. Or the I mean, like, we'll go over the details after the exam on Monday, so to not combine like too much information. But I mean, we like, it's like, it has a bigger emphasis on the integration stuff. So but besides that, yeah, we can talk about it after Monday, maybe. Just give me a second. Okay, so as I was saying, for today, the last, like the first 20 minutes, like next 20 minutes or so will probably be about finishing 16.5, and that's on the midterm on Monday. Then we'll have some remaining time to talk about 16.6, which is not on the midterm. So I'll let you know when, like, the class like enters new material. Like, the only, like, there's not too much you need to know about 16.5. It's like a fairly straightforward. What that section is mostly about is about parametrizing surfaces, which I sort of mentioned very briefly at the end of the last class we had before the break. So when you parametrize surfaces, like, essentially what that means, like, is very concretely that you write the position vector of a surface, well, of a point on the surface, in terms of two variables or parameters. And the way in which you do that is essentially, we did some examples last time, but basically what you do is you use the equation of the surface to sort of eliminate one of the variables. So like the way you do this is like to find a parametrization. You use the equation of the surface to find a relation between X, Y, and Z. And that way you can replace, substitute, or write one of the variables in terms of the other. And so you can write one of them in terms of the others. Okay. So like I think we may have mentioned this example briefly last time, but it's just worth doing it again. It's a good motivation for what we're about to do. So an example we discussed, I think, was the cone. Let's see. Okay, so again, if you think of the cone, it literally looks like this, looks like a cone. So this is like what the cone looks like. And then what you do kind of is you choose your favorite point on the surface. Like you choose a point X, comma, Y on the surface, comma, Z. And so you see the point of a parametrization is that you use like the equation of the surface, in this case, the equation of the cone, to like sort of just end up working with two variables. So like the most obvious thing that you can do here is like just take advantage of the fact that Z is already written in terms of X and Y. So like the idea is like for a point on the surface on this cone, like the moment that you know X and Y, you know what Z is supposed to be, and it should just be the square root of the sum of the squares. So this would be like a parametrization in terms of X and Y. Is that making sense?
Yes. Yeah.
Now, but like again, like the point is that there are other alternative parametrizations you can use, because like you also know that X, if you want to use polar coordinates, it's like R cosine of theta, and Y becomes R sine of theta, right? And so what do you think happens with this equation of the cone if you switch to polar coordinates? What does this become? What does like square root of X squared? Yeah, it just becomes R, right? Good. And so again, like the key fact is that you only see two variables, right? And so this would be called, this is an alternative parametrization of the cone in terms of like R and theta from polar coordinates. Like the important thing is that whatever parametrization you use, like there only need two variables present at a time. So here the parameters are X and Y, and here the parameters are R and theta. Okay. where we're headed, and this is like the last topic for the midterm on Monday, so I'm about to write this down. Like the objective eventually is to just like say, well, like how do you do like an integral, you know, so far, sorry, like maybe just as an aside, like so far the integrals we have been doing, like when they were like double integrals, they were like integrals for a region on the xy plane. Sort of what we're going to do now is to do like an integral over like a surface. So it's like instead of being called like surface, like double integrals, they're called surface integrals. Okay, so the only thing that you have to notice, this is very similar. You should think of this as being very similar to the stuff about the Jacobian, which, by the way, it's on this exam as well. So if you remember like the Jacobian stuff, what you could do was like a picture on a plane, right? Where, oops, what happened? Sorry. Oops. You let me stop the shit. Is it? Oh, resurrected. Good, good. So don't touch the cables. So I don't know if you remember. When we were talking about like this section about the Jacobian, that you could make like draw like a UV plane, right? In this case, say that you're looking at the parametrization in terms of R and theta, right? Then you're looking at a parametrization where the parameters, like instead of using like UV plane, you can make like the theta R plane, right? Now, what values, like think of this as like we were like, imagine that we're going to try to set up like a double integral that takes place over the cone, where the region of integration is the cone itself. So what values does the angle theta take on a cone? What values would you choose for theta? Yeah, it's sort of 0 to 2 pi because like the cone sort of rotates about the z-axis, right? So all the small, like interesting stuff happens on the between 0 and 2 pi. And then like the values for R are a little bit more interesting. R is like you know, the distance of a point to the z-axis, right, in cylindrical coordinates. So if you include the vertex of the cone, right, this happens when R equals 0, right? But so the cone itself, it is, well, right, that's the thing. The cone itself is actually like infinite, right? Like it is sort of like an accident that I cannot draw like an infinite surface, but you should imagine that the cone just like, you know, if you think of a cone, you can sort of draw it as big as you want, right? Like you just keep like open it. So in order to have like, so strictly speaking, if you wanted to, you know, if you wanted to like parameterize the full cone, right, you would have to put like an infinity here, like just to say that R can take any value, if that makes sense. The problem of doing that is like, it's like an improper integral, which we're really not trying to do in this class. So essentially what you do is like, you can chop off, like, you know, imagine like just like cutting the cone with the plane that's parallel, like say to the like XY plane. So it's just like it's trying to draw like a cone inside like a room, right? So at some point the cone, if it keeps growing, would just hit the roof and it can stop, it can no longer grow, right? So imagine that I just cut it at height z equals 3, right? So what is like the height is c equals 3, right? Remember that under this parametrization, r equals z, right? So what we find is that r has to be between 0 and 3. Is that making sense? So like here you have r between 0 and 3. So in the cone, in the UV plane, or in the theta r plane, what like, oops, everything chaos. So like many things open at once on my computer. So in the r theta plane, like you have this like rectangle, or yeah, I guess it's a rectangle. And like any point, like the idea is at any point, you choose your favorite point on this rectangle, and that would give you like a corresponding point on the cone. So if you want, let's say that this is.
So this is like a change of variables, but in polar coordinates, I guess.
It would, like in this parametrization, it's like, yeah, it's like a change of variables. In polar coordinates, it's just that now the region of integration, right? It is not like a region on the XY plane, right? Like the region of integration is the cone itself, right?
Got it. Okay.
So, but right, it's like doing some sort of polar, like you're still like, what I'm showing you here is like the values of the parameters. And like I'm just saying that maps, like if you choose like a point, think of this like, you know, again, like a map. And so like, you know, like in the real, like in the past, well, and I guess still true today, like when you carry like a map, it's sort of like 2D, right? Like a 2D representation. Yep. So like here, like what I'm saying is like in this map, a point on this map corresponds to a point on the cone, basically.
Yeah, and the cone is a surface?
The cone is a surface. Yeah, I actually have a cone here. Oops. And r equals 3 was randomly chosen. Correct. Yeah. Everyone sees the cone? So yeah, it's just to, and like say here's r equals 3, and then if you want to cut it, then you get r equals 1, like, or somewhere. So yeah, you can kill the cone to some extent, because otherwise the cone is infinite. So good. So why is this you like, and so like here's something too that happens. So imagine that like imagine that you want to move like what I'm saying is that if there's like a point, like if a point gets mapped to a point, right? If you imagine that you want to look like you take like a segment on this parameter space, right? So imagine that this is like the value, like all the points where theta equals pi over 4, right? And so you have this orange line here, and you could ask like, how does that look like on the cone? So just to make this more clear, like I'm going to choose this parametrization, right? I'm not going to, I'm just going to replace theta with pi over 4. So if you put pi over 4 here, what do you get? You get r, what's cosine of theta? That's 1 over root of 2, right? So you get r over root of 2, r over root of 2, and then r. Okay, so let's go back to GeoGebra. Actually, this is, I did it already on GeoGebra. I don't know, can everyone see the animation? So you have the cone here, right? And I have this equation r over root of 2, r over root of 2, and r, right? That's like the parametrization of the cone that we get when we fix the value of theta to be pi over 4, right? And then like what happens, like as you move, as you vary the value of r, does everyone see the r increasing? Everyone sees the line, like it's like the segment that gets created.
Yep.
So like, and let's say I got up to 3. So essentially you sort of create like this, and here's like z equals 3.
So that's a piece of a cone essentially, right?
Right, like that's a piece of the cone, right? Like the roof is here. But like what I'm saying is that what ends up happening from, hopefully this animation makes clear, is that if you choose like a line or a segment on this, in this parameter space, that sort of gives you like some sort of curve that you draw on the cone. So that's
So now
like,
that if there's two variables, would that mean that the integration, what would be the dA?
Oh, right. That's
Value?
what we're about to find.
Okay.
But like what I'm saying is like, and similarly, like the point, so like different, like the is like, in this case, like different orange lines map to something like this. And the other one is like the ones that are sort of parallel, like with fixed value of R, right? The ones that are like with fixed value of R, they actually map, in this particular case, they map something like concentric circles. And so the idea is that you start drawing like a bunch of curves on the cone, okay? And why is this useful? Because, and let me go show you something else. So there's actually, I don't think we have ever used it in this class so far, but there's something called Wolfram demonstrations project. I don't know if you have seen it, or maybe I have mentioned it once or twice in this class, but like here you can like find like cute animations of things. So there's like one that's very nice for surface parametrizations. So I already downloaded it, but it's this one. It's like an extent. It's like, this is grown up Wolfram Alpha, if you want to think about it. This is like the adult version of Wolfram Alpha. So if you do this, like, let me open like let me open this here, and it's called good. Okay, yeah. So you get like, when you open this and download it, you find like, you'll find some, like you get like something like this. Like that's what this animation is about. So for example, like here is like this version of the UV plane, right? Like, which I was calling theta R plane in a while ago, but like in general, depending on what names you give the parameters, there, this is just called UV plane. And so you see like, there are like these like lines, these like, I think I can, there's like this red line and blue lines, and they correspond to some, like to a bunch of curves on the surface, right? And so if you choose like a tiny, if you choose like a small rectangle on the UV plane, right, that sort of maps to something which is not quite like a rectangle on the surface itself, but it's like a piece of the surface. Is that making sense? Maybe on the sphere it's like a little bit more explicit. So like you can move here. Everyone sees it here. Like I don't know how big the animation looks like on your computer screens, but like again, like you get like, you choose like a small rectangle on the UV plane, right? And you get like a piece of sphere, which can change in size. Like, so I don't know if like this actually should remind you of what happened in the Jacobian animations also, where we had like maybe like rectangles of fixed size here that would get mapped to some weird shapes on the region, on the 2D region, right? It's just not now that like the 2D region is just like a piece of the surface. Is that making sense?
Why why does the plane on the sphere, why is it a plane? Why is it not like mapped to the actual surface of the sphere?
Right.
Is it
This is
tangent?
just like an accident of the animation. Like the idea is like, you want to think, right? Like you want to think that this square is really, really small, right? And so the idea is like the difference between the actual piece of the sphere that you get mapped to and this piece of tangent plane is very, very small difference, you see? So it's just that the animation is found that easier to, you know, to just represent like the tangent plane. So like it's, but right, like the idea is like, yeah, in this animation, it looks like that is not on the sphere. What you should draw, like think is that it's actually trying to draw something on the sphere. It's just that like the difference between that piece of the surface and the tangent plane at that point is very, very, very small. So here you can do.
So the DU/dV represents a typical piece of the surface.
Right.
Got it.
Yes, it represents like the UDV represents like a typical piece of the surface, but like the takeaway of this animation is like you sort of distorted the area, right? So on the left-hand side, right, on the UV plane, they all these rectangles like sort of have the same area, right? Like the ones that I'm choosing, but you see like the different like pieces that you get on like on the corresponding surface can have different sizes, right? So, and that's like if you see downstairs, like that's sort of what this is trying to tell you, that like, you know, you can choose like that there's
but is it still a multiple of what we're defining in the square?
Right.
Rectangular.
Yes, you are going to have to multiply by a correction factor, right?
Got it.
And this correction factor is sort of like, again, like the grown-up version of the Jacobian. So, and that's like essentially what I'm about to write. Like, and this is all that you need to know for the last part of the exam. That there's like a, you know, just as in the case of on regions on the XY plane, like there's something that multiplies the areas in the UV plane to get the correct area in the region. And so here there's something similar. You choose like an area on the UV plane and you multiply by something and you get the correct area on the surface. And that factor is called the Jacobian again. So the whole point like of what I was doing this is that essentially you sort of approximate it with parallelograms. And I don't know, like we did this a long time ago at the beginning of the semester, but there was a formula for the area of a parallelogram in terms of a cross product. So that's essentially what the Jacobian is in this case. So that's essentially like what that gives you like a rescaling factor. So let me just write that down. And that's like, this is actually like the last formula for today. So like, I like to call it surface Jacobian. Sorry, the last formula for the exam. So is that call it the surface Jacobian. Again, is that like the idea is that if you had like a piece of surface, think of a piece of a surface as some sort of blanket or string, a membrane floating in space. So you have like these sort of like curves that you get by drawing them on the UV plane, but they just become some curves on the surface. Okay. And then like you just focus your attention on a very small, again, they're not quite rectangles, but if you did this, if you chop this up very, very thinly, they sort of become better approximations to rectangles. So, or parallelograms, that's like the better word in this case. So when you choose like a piece of this size, sorry, let me use a different color. So there's like a small piece of area, which we can call delta S because it's like a tiny piece of the surface S. So this is the surface, which I'm calling S. So delta S is just like a piece of the surface, right? Like a super small piece. You cut it with scissors or whatever. So this is like a tiny piece of surface, tiny area of the surface. But again, like the idea is that you sort of approximated that with like those parallelograms that you were being shown on the animation. And the area of a parallelogram is obtained from a cross product. So like long story short, like it's like the idea is like like the cross product that you use to compute the area is just like the one of this partial derivatives. So I mean, dvdu sort of like the thing that you would expect just like from the area of a rectangle on the UV plane, and then you have to multiply by this rescaling factor. And so essentially this is this thing is like the surface Jacobian, if you want. So it's just and in fact, if you did this, like it actually gives you back the formula for the Jacobian that we saw before, although it's not too important like right now to see that that does happen, but it does occur. So and so like the last formula for the exam, and this is like really it. So this is the last formula for the exam. Let me write it. Is that if you want to find the area of a surface, like for this exam, like the only thing that we care about is like to find areas of surfaces. It's just the integral of like all these pieces delta s, or it's just like the sum of all these pieces delta s, and so it's like an integral. So it's like an integral of the surface Jacobian okay.
And the surface Jacobian is defined as a parametrization of the given function.
It is, I mean, it is defined in terms of the parametrization of the surface. So here, R of u comma v, I'm about to do it in the example for the cone.
Yeah. Okay.
Is a parametrization of the surface.
And so we just take a cross of the partials.
Yes, exactly. Right. Yeah, let's do it for the cone, in fact. Let's go back to our cone example. So back to the cone. If you remember, the cone that I gave you was like at this plane of height 3, because we didn't want to work with something that was infinite in size, right? So the parametrization of the cone in terms of r and theta was r cosine of theta, right? R sine of theta, and then r. So here, this is like u and v. Let me, in fact, like, right. It doesn't matter which one you call, you know. It doesn't really matter which one you call u and which one you call v. Usually u is sort of like the one that you draw horizontally. And so in this case, like theta is like u, but I mean, like it doesn't matter, like again, like there's no necessarily obvious convention which one is like u and v. Like the whole point is like the whole point is that there are two parameters, and so you can find the partial derivatives of this parametrization, which with respect to each of the parameters. So what by that I just mean that, for example, if you take the partial derivative of this with respect to theta, that just means to take the partial derivative of each individual entry with respect to theta. So you get minus r sine of theta, r cosine of theta, and then 0. And then there's a second parameter, and so you can take its partial derivatives with respect to r as well. And you find here cosine of theta, sine of theta, comma 1. Is that making sense?
Could you have, like, hypothetically speaking, more than 3 entries?
No, here there will always be 3 entries because the surfaces will always be like
in 3D.
In 3D, yeah. Although it's true, like you can actually generalize this, but it's like the formula needs to change a little bit because you cannot really define the cross product per se. The cross product is only defined for 3 things with 3 entries. But there are like ways to fix this, like for more, But yeah, in this class, like 3 entries is sort of like the maximum number of entries. So far so good. Any questions? So like it's just find the parametrization, find the partial derivatives of the parametrization with respect to the parameters. And so you get 2 vectors. You always get 2 vectors because there are 2 parameters. And so you take the cross product of these 2.
I have a question.
Yes.
So before we switched into polar coordinates, we parameterized the equation with respect to x and y.
Yes.
Even though the math would be a little bit uglier, is that still a valid parameterization? That
you can also find the area using x and y as the parameters, correct?
Okay.
It's just that the bounds, like, the bounds for the cone, like the thing, like if there's not too much of a difference, like, like instead of doing like the partial derivatives with respect to theta and r, you would find the partial derivatives with respect to x and y, right? Like that's not too different. Setting up the integral is a little bit more annoying for Cartesian x and y, because the bounds, like they sort of look a little bit uglier in Cartesian than in the cone case, right?
Right. Okay.
So is you sort of adjust in that sense, it's not that different from doing like a double integral, right? Like the reasons when you do it in polar, because like the region looks better in polar. Here, like it's just that the bounds or like the surface itself like just works more nicely with polar in this case. And so
I understand. Okay.
If you do this cross product, like this is like an ordinary cross product, you do it like as always. And so you find like r cosine of theta, r sine of theta, and then negative r. That's what you should get. After you do some simplifications, that's a cross product. This will actually be useful later because, like, I don't know if you remember, like what we're doing is sort of like the analog of, let me just write it here, like of A cross V, right? We're doing like the cross product of 2 vectors. And I don't know if you remember, like the cross product is supposed to be perpendicular to the plane, right? So essentially when we do these cross products, we're finding like a vector that's perpendicular to the surface. And for now, this is not useful information, but let me just write it.
Become like a vector field at some point?
It does become like some sort of vector field, but perpendicular to the surface. So for example, here, if you look at the cone, right? My iPad pen is like the vector. And so it's always pointing, like the one that you find when you do this cross product is always one that's perpendicular to the surface. So it's like an alternative, because we had found in the past like vector perpendicular to the surface by taking the gradient of the equation, if you remember. This is like an alternative way to find like the vector, just like using a parametrization. And
was it, when we found it previously, was it perpendicular or was it along the surface?
No, it was perpendicular because we used it for the tangent plane, right?
Right.
Equation,
the direction of the steepest descent.
right? And so again, like if this were like a sphere, like these vectors that I'm finding are like always perpendicular to the sphere. So again, this is not really information right now that's useful, but like this, like think of this vector, this cross product, as a vector perpendicular to the cone. Okay. And the Jacobian, or the surface Jacobian, is essentially like the norm, the magnitude of this vector. So And so you get two r squared, right? Because the first one just gives you r squared, and then there's an r squared here, and so you get root of 2 times r. Is that making sense? Any questions? Good. And then like the area of the cone is just like the integral of this surface Jacobian. So the cone area, or the area of the cone, is the integral of this surface Jacobian, dr d theta. And so theta here goes from 0 to 2 pi. We had found the values for the parameters before, right? And r goes from 0 to 3. And so, I mean, like now this is like an ordinary double integral. It's indistinguishable from all the double integrals you have done so far. And in this case, you just find 9 root of 2 times pi. So that would be.
Excuse me, I have a question.
Yes.
So since you converted to polar coordinates, why isn't there an additional r term in the integral?
Oh, right. Like the thing is like, that's always a question that pops out, like a good one. So the reason why is that when we did polar coordinates, right? In polar coordinates, this r dr d theta, right, is really secretly like what pops out when you do the surface Jacobian, you know, in a sense. It's just that we do it all the time. So you sort of, it's easier just to give it as a formula. But it is, I mean, it is what you would find if you did the surface Jacobian stuff. Is that okay? So like what I'm saying is like,
So the same concept would apply to like if we converted to spherical coordinates instead.
right, yeah, exactly. So like the thing is like before, if you had like a region on the XY plane, right? If you were to parameterize this in terms of polar, right? It's like r cosine of theta, right? R sine of theta. And now this one is 0 because it's on the XY plane, right? So it's a little bit different from the cone, because in the cone case, like the third entry was not necessarily 0. But so when you do the partial derivatives with respect to, like, let me do it again with respect to theta, you find minus r sine of theta, r cosine of theta, and then 0. And then when you do it with respect to r, you find cosine of theta, sine of theta, and then 0. Right? And so again, like here, when you do the cross product, in this case, you find 0, 0, negative r. And you see like the norm of this vector, it just gives you r. So that's how the r from polar pops out, if that makes sense. So
Okay.
you don't have to, like, if you were to add it by hand, you sort of are duplicating its effect, because it's already being taken into account. Like the surface Jacobian is that, but it's just like a version that works not just for polar, but other things as well.
Okay, yeah, that makes sense. Thank you.
Then, well, at least this midterm does not have triple integrals, and triple integrals tends to be the hardest part of the course. So in that respect, like you could find it easier. But you're close to the end, so there's no reason to drop your guards. Is that making sense? Any other questions?
That's good.
Good. So, and again, like it's not right. Like for like here's like a cute example we can do. So just let me go back to GeoGebra. Now imagine that oops. I don't know if you remember like this saddle stuff, which which we talked about when we talked about saddle points, like
Yep.
and so you have this surface, right? And for some reason, like you're interested in knowing this, like let me write stupid rotations. Where is the so you want to know like the stuff of the oh okay, I'll do it with, I mean we could do it with that one, but then I won't be able to draw like a nice picture on the iPad because this one always kills me. So let's, okay, this is more friendly. So we have like the salad bowl, right? And then you want to know like the part of like the area of the salad bowl which is between the curves y equals x and y equals x squared. Okay, so I don't know if you see it, like these two curves, like, or surfaces cut the salad bowl into pieces, and then there's like this green area trapped between the two surfaces, like these two cuts, right? And so we're going to try to find this area. And again, I think probably because the salad bowl, okay, let me do it. I'll invert it so that it's like more like obvious what to do. Okay, so I just want to know the stuff that's above the XY plane of the salad bowl and between these two surfaces. So let me write that down to make this.
Would this mean that you would again start with the bounds, defining the bounds, and then parametrizing them into our new coordinates?
Well, in this, like I always recommend parametrizing first, and then you find the bounds. The two processes are independent of one another, but the parametrization, I find it less like confusing if you want. The bounds, like then you just worry about the bounds. But let's do another example. So stupid cable. Okay, good. Stops working at times. So let's try to find the area of the surface. Well, let's do 4 minus x squared minus y squared. Okay, find that area of the surface of the part of the surface. Let's put it like that. So which is above the XY plane. So it has two conditions. It is above the XY plane. And then between the curves, so what I'm trying to say is that let's start to do this. So this thing again is like some sort of inverted salad bowl. So imagine just drawing that here. So that's the graph of the surface. And then you have this you have the line y equals x, which is sort of like at 45 degrees. that when you lift it, right, into this plane, it just cuts the salad bowl somewhere, right? And then you also have the parabola, right? Y equals x squared. And when you lift this one, like when you draw like a wall for that one, it also cuts the, this is a little bit harder to draw. Sorry, oops. Let's see, you just draw it and it cuts the oh, it cuts it somewhere like this. So there's like a piece, I think that's how we should cut it. So there would be like a piece of the surface of the salad bowl that's between these two curves. Is that making sense? It's kind of difficult to visualize. Like if for something like this, since this one is complicated, like you'll probably be given like a picture. But like, is that like the idea clear? Like you're just looking at part of the you're looking like sort of at the part of the surface that got trapped between these two cuts. So again, and in fact, it's useful in this case to draw the two curves separately on the XY plane so that it's not too confusing. So here was y equals x. And then here was y equals x squared. So there was like this region on the XY plane. And we're just looking at the stuff of the surface, which is above this piece of on the XY plane. So we're looking at the part of the surface, which is above this region. Is that making sense? And so, like, again, like you just have to find the parametrization. In this case, the parametrization that's most useful, but your parametrizing is the salad bowl, right? Like this surface. So in this case, the surface is being given in terms of x and y. Is that making sense? So that's the parametrization of the surface. And then you just do the same as we did last time. By the way, in this case, it's more useful to work with x and y directly, just because like the bounds will be determined by these two curves, and those are easier to find, like, you know, in Cartesian. So when you do this, you get what? 2x, 2y, and then 1, I think. Well, it depends on what you chose for the parametrization. In this case, it's x and y because those are the parameters that I chose. If you had chosen theta and r, then you would have to do it with respect to theta and r, but then you have to write everything. So yeah, you can always choose. But the choice depends more on the bounds. So you see, like the bounds here will be the stuff between these two curves for the values of X and Y, and that's easier to describe in Cartesian than in polar. So yeah, it's like a combination of what work. It's sort of like you know, it's like a dialogue of, you sort of look like something that works for the equations of the surface, but at the same time you also have to keep in mind that you want to set it up with bounds. So both like they're like two impulses. You have to work with both of them. And so the surface Jacobian in this case is just 1 plus 4x squared plus 4y squared. Okay. And so the area of this piece of the surface of this piece, so the area would, again, is like the integral of the surface Jacobian and then well, in fact, this and then you have to describe this region using like for example, if you use like vertical arrows, then it's between x squared and x, and then from 0 to 1. Is that making sense?
Yeah.
And now this one is actually one where probably you would not be able to integrate easily. I mean, it is possible to integrate it, but it's too complicated. So like, I mean, if you look at practice exams, sometimes like they would just ask you to set it up. So this is like an example where you are just asked to set it up. So this would be the setup, for example. Like typically the practice exam questions, it depends on the problem. If it's like an upload problem, then like you probably can use any parametrization that you want because a human will check it. If it were like a non-upload problem, then you are told which parameters to use usually, because like, you know, you cannot like program MATLAB to recognize like infinitely many options. So like, depending on what type of problem you may. So I'm saying like it could be like the case that you choose the parameters that you want, or sometimes we'll just tell you which parameters to use. So in this case, we would have said like use X and Y as parameters, or we would have said like use R and theta from polar coordinates as parameters. Well, if you had wanted to like, I mean, if you wanted to do it as a triple, right. If you had if you had done like something like this, what, like 4 minus x squared minus y squared. I think this is what you're saying. If you do something like this, then that would be the volume of the paraboloid between these two curves or cuts, right? Yeah.
And when we take the gradient of this, that's when we get to the surface of that volume.
Right. I mean, the thing is like, also like, I mean, the volume, like, it's kind of like an accident that sometimes you can write the volume as a double integral by putting like the equation of the surface as like the function, right? Like usually, like if it would be nicer like to write it like this. This would look nicer in my, like, this is really how it would be better to write like the volume integral, right? It's just that when you do the integral in Z, like you just get back the function, right? So it's like volumes are really always triple integrals. It's just like one of the like the first integration becomes so easy that you can write it like as a double integral almost immediately. And yeah, but if you wanted like the surface integral, I mean, it's not the gradient per se, but it's involves the derivatives of the equation. So with this cross product business. So, but yeah, so the gradient does not appear quite like the gradient does not appear directly here. I mean, kind of it does. Okay, right. It kind of does because, but that's not how we're saying it. But yeah, like because this is like a vector perpendicular to the surface, and the gradient is also like a vector perpendicular to the surface. So that's how they are related. Yeah, I suppose so. So yeah, you could also use like the norm of the gradient, but it's better like for other reasons, like we're doing it from the parametrization directly because it's more convenient for other stuff in the class later. But good question.
Are we going to do another example?
Yes, we're going to do another example, but just with a slight improvement. It's still the same story, but
can you label the steps, like how we're going about this solving?
Right, like, well, there's essentially two steps. This basic like the steps are just like to find the parametrization if you want. Let me write it like as in terms of u and v, because I don't necessarily know here if you use x and y or r theta or something else. So step 2 is to find this, like, you know, again, like you can break it in as many as steps as you want, but like you find the partial derivatives, then you find their cross product, right? Then you find the norm, right? Or well, yeah. So you see, like the first 4 steps involve the parametrization only. So that's why I say that it's better to start from the parametrization. And then the area is just like the integral of this thing.
Now, when you say find parametrization, that's we're finding the parametrization of the surface.
Right, of the surface, yes.
And say in the previous example, if we, hypothetically speaking, if we were to convert it to polar coordinates, would that mean that the bounds would also need to be converted to polar coordinates?
Yes, correct. Like, right. You would have needed to describe like this region. Sorry, just to go up for a second. You would need to describe this region in polar, which is a little bit, like, it's a little bit messy. But yeah, so you would write, you know, it's like you rewrite each equation in polar to find like the bounds for r and theta. Yeah. Is that okay? Let's see. So far so good. Any other questions?
Could you hold on here for a second?
Yes. So the next step, like, let me just write here, section 16.6.
Thank you.
So so the next step is just like, again, now this really is for the final exam, but essentially it's the same that we have been doing. So it makes sense to include it right now. The next step is not when you want to find the area of the surface, but rather you want to like do the integral of a function on the surface. So like now the only difference that we're going to do is like, say you want to integrate a function over the surface. Usually this is written this way. So this just means like the integral of f over the surface. And essentially, basically, like the difference between what we're going to do right now versus before is that before we didn't have like a function. Now we're just putting like a function on the integrand. So you just do all the same steps, except that now you just have to rewrite the function in terms of view of the parameters. So like what I'm saying, like what I'm trying to say is that what we will do is like basically the same as before. So this is the same stuff, same as before. And here is the function f, but just rewrite the function in terms of u and v. And here, like are again like the bounds for v and the bounds for u. So it's
Now, what does adding that f give us?
well, it depends, like, because like for example, like imagine that you could think of f as being like some sort of like what people call like a surface density. So like think of f as being like mass per unit area, right? So if f like, so just like as an example, like if f is like mass per unit area, right? Then the total integral of f, right? It would be like integrating like a density function over the surface. And so the integral of f, the f would be like the total mass of the surface.
So is that kind of like before we found the normal vectors which are perpendicular to the surface along the surface, and now it's kind of the magnitude of that vector.
The thing is like, well, f, so you don't necessarily need, like f can be thought here like as a scalar. You don't have to think of f as like the norm of a vector. You can always kind of do that if you want, but
no, I meant the norm of the vector was what we found with
this one,
Jacobian.
right,
Yeah.
like,
and now the f would be kind of like the magnitude, right? The length of that vector.
well, the thing is like this f, actually you should think of it as being like completely unrelated to the Jacobian itself. It's sort of like when, similar to when you were doing like imagine that I had given you like a function and I asked you to integrate it in polar coordinates, right? There's like this factor r d theta that you would always put, right? And then what you would do is like just adjust the function in terms of polar and put that into the integral, right? But depending on what the function was, like you would just put like different things, right? So if this had been this, like you would put like, and then like r squared cosine of theta sine of theta. So like we're doing something kind of similar, where like I just gave you like a random function which has nothing to do with the surface in principle, and then you just integrate it. Is that making sense?
Yeah. Okay.
So it could be related to like something about the surface, but it may not be related to it. I mean, like what I'm saying is that in practical examples, like you may think of f as being like some sort of density function or whatever. And so in that case, like this would compute like the total mass of the surface, or like if this were like some charge, electric charge per unit area, this like you would think of like this would give you like the total charge of the surface. So, but like, let me do an example. Like the idea is that it's not different from like the stuff that we have been doing up to this point. Is you just have to include like a function. So let's do, and we can finish today with this example. So let's say you want to integrate a function. In this case, it would only depend on two variables. But let's say I want to integrate this function over the cylinder between 0 and 3. So let me try to draw the picture. So you have a cylinder, right? Here's the cylinder of radius 2. And we, again, like the cylinder itself is sort of infinite. So we're just going to look at the stuff of this, the part of the cylinder, which is between the plane z equals 0. So here's z equals 0. And z equals 3. So again, you have like this infinite cylinder and you just cut it up in 2 places to get like a finite cylinder. Okay, so the surface itself is a cylinder. And we're just looking at the stuff between those 2 planes. And on that cylinder, we're sort of going to integrate this function x plus y squared. So again, like the steps are essentially the same that I just wrote. So the first thing that you should do is to parametrize the cylinder. So this is like step 1. So how would you parametrize the cylinder here? What can we start doing to parametrize it?
Cylindrical coordinates.
Cylindrical coordinates.
Good. Yeah, it's a cylinder, right? Like sort of, it's almost baked into the name. So if you switch to cylindrical, you put r cosine of theta, then you put r sine of theta, and then you put z. But so far, you see 3 variables, and you cannot do that, right? So somehow we have to remove one of the variables. And so which of the 3 can we kill in this parametrization?
The z.
Well, not really, because the z is changing, right? What's the equation? Like, think of the cylinder itself, right? Like the cylinder is x squared plus y squared equals 4, right? That's the equation of the cylinder.
R. Get rid of R.
This becomes r squared equals 4, right? Which becomes r equals 2, right? So that means that on the cylinder, actually, r is the one that goes away and just becomes 2, right? Is that making sense? So you always use it, just go with the equation of the surface and see what it tells you about the variables.
Yeah, makes sense.
And so this is like a parametrization in terms of theta and z, right? Because those are the only 2 variables that survive. And that sort of makes sense, because if you're on a cylinder, right, like you can imagine that the angle changes, right? As imagine you are like an insect or an ant walking on the cylinder, right? So what is changing if you are walking on a cylinder? You can change your angle, or you can also change your height, but you cannot change your r, because a cylinder has fixed r, you see? And then once you do that, like the next steps are like essentially the same. So you find the partial derivatives with respect to theta and z now. And then you find the partial derivative with respect to z, and you get 0, 0, 1, right? And then in step 3, you had to do the cross product, right? And well, I mean, it's like the usual business. So if you do this cross product, you get 2 cosine of theta, 2 sine of theta, comma 0. And for step, if that's how we were counting them, was to find the norm of this thing. Well, which gives you, okay, I mean, it's really 4 cosine square of theta plus 4 sine square of theta. So that gives you 2, right? So in this case, it gives you a constant, which can happen. That's totally fine. Okay. And if you want here, like this is the new step. So this is a new one, which is just rewrite the function f in terms of the parametrization. So f was x plus y squared, right? But in this parametrization, what is x? X is 2 cosine of theta. And what is y? Y is like 2 sine of theta. So does that make sense? Of essentially what you do is rewrite the function f in terms of theta and z. In this case, there was no z appearing, but that's fine. But I'm just saying, like, you just have to replace x and y with the formula given by the parametrization. Is that okay?
Yeah.
And so finally, the integral. So you see, like, integrating this like function f over the cylinder would be what? F was really just 2 cosine of theta plus 4 sine square of theta. That's what f becomes. And ds in this case is always, remember, like the partial of r with respect to theta. Oops, ran out of space. So let me put it. But it's just that we found in this case that this norm was just happened to be 2 in this particular example. Right, that's what we found here. And then you just have to give me the bounds for the cylinder, right? So what are the bounds for theta? Say that theta on a cylinder goes from 0 to 2 pi, right? And what are the bounds for z? Well, if you look at the picture, I told you z, we wanted it to be between 0 and 3. So that's like those are the bounds for 3.
And again, will we be able to, will we be asked to calculate this or just set up the integral?
Again, it depends. Like usually, like it could be, well, again, like this part per se is no longer for this midterm because it had like a function, right? Like, so the only difference between what we did before and now is that now we're also giving you a function. But in general, like if it's like an non-upload problem, typically it's more like setting it up. So you could set it up and that's it. If it's like an upload, you may be asked to compute it, right? And if you compute it, in this case, like it should give you 24 pi. So like kind of, you always have to be ready for both situations. But again, at least you will always get to the part where you have to just write how you should set it up. And then like if we want you to finish it, it depends more like if it's upload or non-upload typically. Okay, so but like you see, like so this part was not that different from what we were doing before. It's just that now you have like this function f hanging around. So on Monday of next week we'll do something else about this section. And then we'll talk about one of the 2 key remaining theorems in the class, which is called the divergence theorem. And then Thursday of next week, we'll finish the material for the course and we'll talk about Stokes' theorem. So we'll be done with the material for the exam, for the final next Thursday. And then the last day of class, which is on Monday, we'll just do like practice problems. No, I'm actually not teaching next semester.
Next Monday is the midterm, right?
Next Monday is the midterm. Well, but
and then the Monday after that is the last day of classes, and then
yes,
final.
The last day of class, so we're just using it for practice problems because we should be done with the material next Thursday. So yeah, good. Okay. Well, yeah. Anyways, I would have taught probably 251 again. So like, but yeah, good. I'll see you all then on Monday. I'll send you a link about extra office hours also for Monday. Yeah, you can also, if you want, you can send me an email and I can just tell you, like, usually an email is easier because I can just either send like part of the code that you need or just like or you can say it here if you want.
Yeah, I just have like a quick question because I typed in the code exactly as it's written on the thing that it like the problem sheet, and it's only showing me like part of the image, and then so I use actually my friend's computer because she's also in this class, and it gives me a different picture. So I'm just not sure if like my MATLAB's not working or something because I don't know if her image that she got is right.
Which problem are you talking about here? Which exercise?
17. I can actually, if I can share my screen and just show it.
Well, I can show you what the official solution should be like also, if you want to, like
Okay. Yeah, that's what it looks like on hers, but it didn't come up like that for me.
Well, I mean, you can always like, it's more like these assignments are more like effort type things. So as long as you sort of like just put whatever you got, that's fine.
Okay.
Yeah. So, but right, it's like someone is pointing on the chat, like it may be necessary, like depending on which MATLAB version you're using, that the code gets rewritten a little bit. But at least this is kind of like how I wrote it for like my MATLAB version. But yeah, you can put like, I mean, it's fine. You can just put like whatever you found.
Okay, thank you.
Sure, no problem. I'll see you then on Monday. In that case, bye.
Have a good one.
You too. Bye.